Differential equations. Often in real world examples, you're observing things and you're noticing rates of change. So in other words, you're noticing derivatives and you want to create the formula that it describes what you're seeing. And so you need to work backwards, the antiderivative, to find this. So an equation in the form like this, I know the rate of change is called a differential equation. And since when you find an antiderivative, we always have this plus c, sometimes we're going to use what's called an initial condition or a boundary condition to figure out what that c value is. So here's some examples. If you had the derivative was 2x, the antiderivative is super easy. It would be x squared plus c. That's called the general solution because that plus c gives all possibilities of things happening. Okay? If we want to find that specific c value, we would have to have some other information. For example, it could tell you, oh, in the original equation, it goes through the point 2 comma 5. Well, if it goes through the point 2 comma 5, that means I could plug in 5 for y, 2 for x, and then I could solve for c and find out, oh, in this specific situation, c would have to be 1. So here we have a differential equation. dy dx is equal to 3x. The general solution for this would be that y would equal 3x squared plus c. Now, assuming that the point goes through, the original function goes through 2 comma 3, could we find the equation? Well, we could plug in 2 for x, plug in 3 for y, and that would allow us to solve for c. And then once you've got c, you could rewrite your equation with the c value. So when a question is talking about the particular solution, they're going to want you to find that c value. We've got a differential equation. We know what the derivative is equal to. So we can integrate this and work backwards. And then plug in your x value and plug in your y value and solve for c. Once you've got c, you can rewrite your original equation. So these differential equations is telling you, you know the derivative. Could you have found the original function? What are all the different ways that this could be worded so that you could recognize it. So the big idea is these questions are saying, I'm giving you the derivative and an initial condition or a boundary condition. Could you work backwards and find the original equation? How could this be written that might confuse you? Well, the slope at a curve at the point xy is 16x cubed minus x to the 4. So here we have to really know what is a derivative. The derivative is a slope of a tangent line. So if they tell you that the slope of a curve at a point is this, they're telling you the slope of a tangent line, they're telling you that that's the derivative. So being able to take your definition of a derivative, understand it in that context becomes important. Once you know that it's that kind of question, solving it is not hard, right? We need to find the integral of that. Add 1 to the exponents and divide. We can plug in our point and find out what C is. Oops, sorry. So let's look at this next example. Here they just give us the graph of the derivative. And they tell us that f of 3 is equal to 11. We need to find f of negative 3. So if we have the derivative, if we had its equation, we could work backwards. So looking at that graph, can you see that you could figure out its slope by doing rise over run? And we already know the y-intercept is at 0, 3. So we could use that to write the equation y equals mx plus b. Slope is 2, y-intercept is 3. And once we have the equation, then we can integrate to work backwards. Oops. So adding 1 to the exponent and dividing will give us x squared plus 3x plus c. We can now plug in our initial condition. We knew that when x was 3, y was 11. And that allows us to solve for c. And now we have the equation of the original function. So finding f of negative 3 would just be a matter of plugging that in now. Now, what if you had the second derivative? If you had the second derivative, could you work backwards to the first derivative? Yes. And if they gave you information and you worked backwards to the first derivative, you could find c. And then if you had the first derivative, could you work back to the original? Yes. So we're going to look at that next. Higher order differential equations. If you had the second derivative and you work backwards, you would get 1 plus c. That first plus c I'm going to call c1. And then if you work backwards again, do you see that you would get a second plus c? I'm going to call that one c2. Sometimes I use c and then d. There's a little bit of a problem if you use c twice in the same question, because one c could equal one number and another c could equal another number, so we can't have the same variable representing possibly two different numbers. So sometimes I've seen this as c and d. Some people like using c and d because they don't like those little tiny numbers. It bugs them. I'm not sure. So we want to find the particular solution. Anytime they're asking for this particular solution, they're asking for the original equation y equals. So if you want to find the particular solution and the differential equation you get is the second derivative, you know you have to work backwards twice to get there. And they give us two boundary conditions, that when x is 0, y was 1, and when x is 3, y was 8. So working backwards once would give us our derivative. And it would have a plus c there. So I wrote c1 for the first plus c. Because I already knew, like, this is, sometimes I really like using the c and the d. Because sometimes you don't know until later on that you're going to be finding it again. And you're like, oh, I've already used c. I can go back and add little ones to it, I guess. Or I can just make the next one d. It's up to you. Oops, I don't want to show you that one next. Then if you work backwards from that one, then you would get an x to the 4. Your c1 would now have an x beside it, and then your c2 would get added. Because if there was a number here, and I took the antiderivative of that, if this was a c1 was a 2, you would get 2x. And in this equation, there are two things we don't know. We don't know c1 and we don't know c2. But we have two boundary conditions. In this particular example, it was a little bit easier. Because what happens when you plug in 0 for x, you can solve for c2 right away. But most of the time, this is going to end up having you're going to have to solve a system of equations. You're going to plug in your 1 point and get an equation with c1 and c2. Plug in your second point and get a second equation with c1 and c2. And then you have to use your skills with systems of equations to solve it. This one was a little bit easier because as soon as I plugged in 0, I knew what c2 was. And then if I know what c2 is, I could plug in 3 and 8. And c1 is a beautiful number, negative 74 over 3. And we can write the particular solution in this case. Looks like this. Okay, I want you to try the next one or two on your own. I'll give you the answer for one of them. We'll start with this tomorrow. And I'll put up the answer for this one in a couple of minutes. See if you can figure out C1 and C2. And you can check it if you're done most of it or part of it.